Hello, everyone. Thank you for attending today. I'm going to present the topic of my licentiate thesis, reducing the distance between requirements and verification in software engineering. The agenda for today, I'll start by presenting the problem that I'm trying to solve, my research, and then background information. After that, we'll begin the research question for my licentiate thesis. Then I will give an overview of the thesis and go through each chapter or studies as I refer to them here in this slide. And then I go also show you the overview every time so we know what am I talking about in what area. At the end, we talk about the contribution and the project. So what's the problem? First, there is a poor efficiency in written requirements communication, like ambiguous or untraceable requirements that increases the distance between requirements and verification. Thus, producing the right product becomes troublesome. Now, we have in software engineering requirements document are the main document of communication between the customer and supplier, and this represent what should the supplier deliver to the customer. Now, these requirements documents are not presented or not written well. This would cause an issue and make increased distance between these requirements, and then they produce the artifact at the end. One of the examples of distance here that I'm trying to focus on is the distance between requirements and the verification. And at the end, if this distance increase, we will not be sure that we are delivering the right product to the customer or as per their expectation and their requirements. Now, we start with what is the distance in software engineering, and what I mean here also in my research. Well, according to Pearson et al., distance is a difference in position or level between entities that requires effort to traverse to accomplish a software development task. Okay, then what does that mean? Well, there is a nice figure here that maybe make it a bit more clear. Well, let's say we have two entities in the software engineering development, and this distance between these entities is the distance that we're talking about. Now, what are these entities? This could be anything, could be an actor, an activity, or even an artifact. And these distances can be affected by change or can be changed by introducing some software development practices. For example, this example, these development practices are not only related to actually implementing the software, but also anything related to the whole development process. For example, during the verification of the code, maybe we could conduct code reviews. And this code reviews is one practice that maybe reduce the distance or changes the distance, could be for more or less. Of course, in this instances, we are reducing or shortening the distance between the artifacts. Now, in their studies also, they have identified, Pearson et al., 8 distances. I'm going to go through them quickly and show what are these distances. So the D1, geographical distance, is the critical position. So the distance between two actors and where they are positioned physically. So this is apparent in more outsourced project where the supplier is away from the customer, and maybe global software development where we have also offshoring. Organizational distance, this is the distance between the positions of actors in the structure of the organization. So one could be on a different level of management, or it could be in different even branches of the organization. Psychological distance, this is the distance in the perceived effort to communicate of one actor to another. This is this distance also between actors, and the way that actors say perceive this effort to communicate is what we mean here. Cognitive level of cognition between two actors. Adherence, reality versus artifacts. Well, in a software product, we usually expect something to be delivered in the software at the end. And this is the reality, what the software can actually do in real life. However, there is a distance between what is in the software that we have at the end and the artifacts that are developed or written. For example, if we're talking about documentation, then what is documented that this product can do, or how it can do it, if we're talking about the manual of this software, and then the actual software, how it can do that. So this distance we call it adherence distance. Semantic distance, the difference in terminologies. And navigational distance, well, not to mistaken with the first distance, geographical distance, this is between artifacts. And we mean here the path that takes to navigate from a source artifact to a target artifact. And the final one, temporal, and this is the time distance of relevant artifacts, when this artifact is relevant or created and when the other artifact is created. Well, now I'm going to present the research questions. RQ1, how to verify software performance using model-based testing. Now, as I said in the title of my research, to reduce the distance between software and requirements and verification. One of the methods that could be used in this context to reduce the distances is model-based testing. And in particular, we identify the research gap in software performance requirements in a way that model-based performance testing has not been explored, and we wanted to explore that and find a solution for that. Okay. RQ2, what's the kind of practice and requirement communication and digital assets verification in infrastructure project? We have, before we go and know if we can implement traceability in a project. And traceability is one also of the practice that can be used to enable reduction of distance. We have conducted a case study to investigate what are the kind of practices and what are the challenges associated with the communication between the customer and supplier. RQ2, to what extent can taxonomy tracing be used to trace requirements to digital assets? And we have also written a sub-question here, what are the lessons learned of using taxonomy tracing? This question is written to also find how can we use traceability to reduce the distance between the requirements and verification. Here's an overview of pieces. So on top, we have the goal to reduce the distance between requirements and verification. And then we have the individual chapters. On the left side, we have the chapter 2, RQ, and that would be used to answer RQ1. And that's in the area of MBT, model-based testing. And on the right side, we have traceability. We have chapter 3 and 4 in that area. As we see, chapter 3 contributes to for conducting chapter 4, and then the end to the goal of my essential thesis. The context of our research is we are investigating natural language requirements, software project and infrastructure projects. Let's start with chapter 2. The aim of the study is to study the current status of model-based performance testing and identify approaches that can be used to model performance requirement and verify the software performance. And now, as we said, we have identified the research gap in this area. There has been many reviews before for model-based testing in general, and then functional requirements or even non-functional requirements, but not to the same extent. Especially in performance testing or model-based performance testing, we haven't found any review in that area. So that's why we conducted this study. And the methodologies that we use in this study, research methodology used in the studies are systematic mapping studies to get an overview of the work done in this area. And we have also collected data from software using software requirements mining, where we look at the set of SRS collection published online. What are the results of this study? Well, from the SMS, we have identified 57 primary studies, and I presented the results, 3 maps. The maps shows the data about performance aspect, the model used, testing level, and research method and contribution and study type. As we found that time behavior is the most studied aspect of performance. We have identified 5 performance aspects. I'm going to present them in the next slide. And time behavior was the most studied one. The software requirements mining, we have found similar result by also finding time behavior as the most specified aspect. In software requirements mining, we look at 77 SRS documents, and out of these 77 SRS documents, 34 contain software performance requirements, and 149 were requirements we have extracted from these documents. And out of 149 requirements, only 106 were actually quantified, because we believe that, as we know that performance requirements specify how software should behave in certain manners, and this aspect of performance should be quantified. Now, after looking at these studies, we found that the goals of model-based testing, mainly understanding these requirements, the written software requirements, knowing what to test, and automate this test process, were not seen in these models. Not all of them had issues, did not identify or didn't actually investigate their approaches for addressing these model-based testing goals. But what we found mostly interesting is that many of these models were actually just modeling the performance of the system as it is. They're not looking at the requirements in many of these models. And this is what our approach is a bit different. So we developed this approach, ProTest, an approach for performance requirements verification and test environment generation. In the left side, we have the model where we have an object. This is what we want to test. And then we have independent parameters as an input and output, dependent parameters as an output. Of course, as we know in the concept, that independent parameter, any manipulation in the independent parameter would affect the outcome of the or the value of the dependent parameters. And in the right side, we have also proposed this taxonomy for performance aspects. We have independent and dependent, and we identified these 5 performance aspects as the ones that were specified and also studied. We have capacity and resource constraint in the independent variable, and we have the independent variable time behavior, throughput, and efficiency. So in a way that if we have So, for example, if we have the capacity of user in software, if this software should support 1,000 users, then any manipulation, change in this number of users would affect the time behavior of the response of the software. Now we jump to chapter 2, chapter 3. Traceability. And the aim of this study is to assess the state of practice of the customer-supplier interface in the infrastructure domain, processes, and challenges. As we said, the main issue that we have is the issue of the communication. And when we want to look into communication, we want to look at the customer-supplier interface. We found the research gap in this area, where there were no studies that investigated this customer-supplier interface and the process associated with that, mainly requirements validation, requirements communication, and digital assets verification. We conducted 2 case studies, and a case study is a good methodology to investigate or to explore, because we conducted an exploratory case study. phenomenon in its natural setting, and we want to see the actual state of practice. We have conducted these case studies in 3 companies, and there were 2 cases, each case 1 project. Now, some of the results from our study in chapter 3, we have identified 14 challenges and also classified these challenges into these areas. We also presented a process diagram for the process that we investigated: requirements validation, requirements communication, and digital assets verification. And this classification, as we can see them, introduced alphabetically. Common RE challenges. These are challenges that were common in requirement engineering and were found also in other research. Many researchers before introduced these challenges in requirement engineering. Project management, these are not really related to only requirement engineering, but it could be in any other project. So they are more related to how the projects are organized and managed. Requirements quality challenges. These challenges are related to the way that requirements were specified. And trace links. Trace links about the creation of these, or the existence of these trace links, and their quality of these trace links between requirements and other. Now, why we chose to study traceability? Well, one of the things that from our goal that it was seen in other studies that traceability reduces the distance between entities in the software development area. Another reason is that also traceability has potential to enable automation. So if we want to automate the test or test generation or change, we want to conduct change impact analysis automatically. If we have traceability, that would be easier for us to implement. We go now to chapter 4. We use now this input from this from the previous chapter 3, and mainly the results about the changes, the existing of changes, and particularly the trace links. And we want to investigate these trace links challenges and find how can we solve that. So we have an idea of using taxonomic trace link to enable traceability between requirements and verification. And in particular here, we were looking at investigating the feasibility of these taxonomic trace links. We have conducted a literature survey and looked at the related work, and we see that the novelty of our research. We have also conducted a feasibility study. That's the main thing that we have in this chapter. We investigate how these trace links and to what extent they are feasible to be implemented in practice. We have looked at 27 infrastructure project requirements, and we use the classification system SP11. The classification system is the taxonomy that we use here. And this is the knowledge organization structure, or as we say, it's classification system in part, and more concrete, is used in the infrastructure project to classify construction objects. Now, what are the results from this study? First, we have found challenges related to association of cost to requirements. In this idea of taxonomic trace links, we have multiple steps, as I'm going to give an example later on. But one of the steps is to associate these requirements with this classification system, as we saw now, the SP11 classification system. We have identified challenges related to the requirement themselves, the way they are written. For example, the requirement could be vague or compound or context dependent. An example of the context-dependent requirements would be if the requirements is not clear about what it refers to just by reading the text of the requirement, but we need to look at what project this requirement is for and what is the document that this requirement is presented in. So the requirements sometimes not really clear about just looking at them and knowing what code to associate for this requirement. Related to the taxonomy, as we saw the SP11 classification system, it's possible that taxonomy itself, it has issues also that also would affect the creation of this association of these requirements with the code from SP11. It's possible that we have similar classes, more than one class refer to the same thing, and it's difficult to make a judgment just based looking at the class themselves. Sometimes we need to look up the parent class or the neighbor class till we be able to know which class is more fit to this particular requirement. As for the alignment, we have varying terminology between the requirements and the taxonomy. So these both also need to be aligned because sometimes the terminology used in this taxonomy are also different than the terminology used in the requirements. And this is actually what we are also one of the distances that we're trying to solve here or reduce is actually this distance between the semantics also. So it's here a challenge for us to have a common terminology actually when we're associating this requirement to SP11 code. Now the other part of the other side of the coin that these requirements associated with the taxonomy, but also the taxonomy should be associated with the destination, which is in this area, the design models that we have in infrastructure projects. So this design model, we looked at feasibility if these were coded by the same classification system by human, but we were investigating if it were consistent, this association of code in these design models. And we found that mostly we looked at a couple of design models and they were actually consistent. But what we haven't investigated if these design models created by the same person or different people, we didn't have the author of this design model. This could be also theoretically. It's possible to verify model using trace requirements. So we have these requirements, and I think we have a typo here. It's 27, not 27. Sorry for that. 27 requirements, 11 were coded requirements, and were found in these design models. And one of these requirements, we found issue in this model that when we try to verify this requirement in the model, we saw that the model that doesn't actually satisfy this requirement. Here I'm going to give an example to make it a bit more clear how we do this association and the idea of taxonomic tracing. So here's a requirement from an infrastructure project. So the requirement says fences should be set up in area A, D, F, or H as shown in the figure below. Exceptionally, may area C used if fence function and effective maintenance can be ensured. Now here's the figure, and as we see here on the left side, this is the area where one can put a fence in an area A, and also D and F and H. So on this left side is where we have a slope, and if you have a slope, you should have a distance of 2 meters. These distances are in meters, and as you can see on top of area B, this 2 meters distance is where one can put the fence after this 2 meter in area A. So the first step is to associate this requirement with a code from SP11 classification system. So here's a screenshot of the classification system. And one of the branches we have here, restriction object, access restriction object, and then we have fence here. So fence is, of course, this is a bit an obvious example that fence is the right fit for this requirement. After we do this association, the next step is to look at the design models and see if this, which were already associated with this similar code from this SP11 classification system, and see if we could actually verify this requirement. And I'm not sure if this is clear. maybe the font's a bit small. But this design BIM model, building information model for a track. The track should be somewhere there. And this green color is the fence, actually. And this blue, this greenish area is the slope. And here is where the fence is situated. And we measure this distance between the slope and the fence. And we found that this distance is not, is less than 2 meters in this area. Now come back to the goal, reducing the distances. Now, what distances are we trying to reduce in our approaches? So on left side, we have the distances, and then we have on top the research areas that we were investigating, or the solution to the problem of increased distances. In model-based testing, we look at the psychological distance in a way that if we could give to the, as we said, the psychological distance is the distance between the actors, and this distance refers to the effort of communication between people. And if we have model-based testing and using protests, as we have seen in this previous example, and this way of verifying the requirements and creating this model, it tells us if some of the requirements are missing. And this way it opens communication between the tester or the developer and the cost requirement engineer or customer in this context, and see what are the issues. Is there a missing requirement, or what can we do to better fix this requirement? As for adherence distance for model-based testing, when we do model-based testing, we increases the chance of automated traceability, automated testing. And automated testing in this concept, we have better way of verifying to the customer that this is a product that would be in reality. And when we look at that, then we have more similar product to what is written and what's in the reality. So we have verified this product as per the requirements, that there's more chance that this is what is in the reality, and that's what its alignment, it aligns with what's written in the documentation. As for temporal distance, the time that usually the requirements are created is early in the project, and the testing or the verification is done way after. Even if it's not, even if we're doing agile methodology, there's also a distance between actually specifying the requirement at the beginning and also at the end when actually we do the verification or the acceptance of these requirements. By enabling model-based testing and automated traceability, testing, then we can automatically generate these test cases whenever a requirement change, and then we automatically verify the system again without taking too long time between the creation of requirement and the actual verification. As for traceability, first the organizational distance. Now this opens the communication between people from different organizations in different organization structure, either between tester and requirement engineers, as they understand what should be tested and how should that be tested. And psychological distance also. It's easier now to communicate with other people because we know what we're talking about, what are the requirements, and what verification for these requirements exist. As for cognitive distance, well, it's possible now when we have also similar a bit to the psychological distance, but in cognitive distance, that we make sure that either if we have different knowledge of the domain, we can still communicate as this taxonomy. It adds a bit of semantic to these trace links. They are not just trace links, but we have also this trace link that has some terminology associated with it, which is the class. Adherence is similar to what we have also in MBT. And we make sure that traced requirements to verification enables a more verified product and make sure that we have delivered what we agreed on. As for semantic distance, as we mentioned, also similar when we're talking about cognitive distances, the semantic distance can be reduced by reducing this similar terminology as a classification system. It can be used to label any kind of artifact, not just requirements, but also test or the test cases or the verification. And then both testers and requirement engineer can be talking about the same thing now because they have the same terminology. As for the navigational distance, the distance or the path, the length of path between these artifacts and how can I get from one artifact to another, which is the actual traceability here, is for us, also could be reduced using traceability as it just connects the both artifacts, and then it's easier for us, okay, just go to this classification system and find what are the other relevant artifacts. This can be also automated by just retrieving these trace links also after registering. And then I want to acknowledge my supervisor, Dr. Michael Unterkamsteiner, and Dr. Krzysztof Unuk. I hope that I pronounced it correctly, but their continuous guidance and feedback. And if there's something correct because of them, if there's something wrong because of me.